Thank you for the invitation. Okay, so I will talk about Artinian Gorenstein algebras and components of the Hodge locus. So first of all, what is an Artinian Gorenstein algebra? So an Artinian Gorenstein algebra is an algebra, a C algebra is called Artinian Gorenstein if it satisfies the following properties. First of all, if there exists a number, sigma, natural number, such that, first of all, for every number e bigger than sigma, L is a graded C algebra. Re is 0 for every e bigger than sigma. The dimension of R sigma is 1. And the multiplication map Ri times R sigma minus I to R sigma is a perfect pairing. Okay, so what our basic example of Artinian Gorenstein algebra is given by Macaulay's theorem. So let's recall Macaulay's theorem. This is Macaulay, 1916. So given f0 to fn homogeneous polynomials in n+1 variables, sorry? Yeah. It's a graded algebra. This notation means the element of homogeneous of degree. So take homogeneous polynomials such that they define an empty set on the projective space. Then we have, they define an Artinian Gorenstein algebra. Then the ring R defined in this way. Is Artinian Gorenstein. Here I forgot to mention something. We say that it's an Artinian Gorenstein algebra of Sokol in degree sigma. Yeah, we denote it like this, Soc R. Okay, so this is an Artinian Gorenstein algebra of Sokol in degree the sum of the degree of fi minus 1 equal to 0 to n. Okay, so what I want to do today is to associate an Artinian Gorenstein algebra to a Hodge cycle inside a smooth hypersurface of degree d inside Pn+1. So I will explain how to do that, and I will explain why this is useful and what can we say about the components of the Hodge locus using this information. Okay, so first of all, before introducing this Artinian Gorenstein algebra, I will give a motivation. So consider pi, the family of all smooth degree D hypersurfaces of Pn plus 1 of even dimension n. Okay, so this you can think of it inside of the vector space of polynomials in n plus 1, n plus 2 variables of degree D. Right? So take a point, any point here, fix a point. So, well, I will do it like this. Take a point here, and the fiber we will denote it by x0. And if you take any Hodge cycle, so consider delta a Hodge cycle in x0, this means that it is an element of the nth homological group such that the Poincaré dual of this guy, when you look at it in the tensor product with the complex coefficients, and then you use the Rham isomorphism to look at it in the Rham cohomology, this will lie exactly in the middle part of Hodge decomposition, right? So consider any Hodge cycle, and then since this family is a locally trivial fibration, so this is a locally trivial fibration, if we take a neighborhood here, an analytic neighborhood, a polydisk, small polydisk containing 0, we know that the preimage in the family, this is trivial. This is diffeomorphic here to the fiber times delta, right? So, and here we have x0. That is the fiber corresponding to 0. Okay. This is a topological isomorphism. This is not analytical. So, well, using this trivialization, we can transport this Hodge cycle to this neighborhood, right? So we have this delta t that will belong to the homological group of xt for every t in this polydisk, right? This is a polydisk. But this doesn't have to be Hodge cycle anymore, right? This is just a topological transport isomorphism. So in this context, we consider the Hodge locus, the associated Hodge locus, is B delta, is the set of parameters in this neighborhood. I will take the germ of analytic subvariety such that this delta t obtained by the formation of delta is still Hodge. Okay, this is the Hodge locus associated to delta. And well, this locus is interesting because there is a conjecture that was proposed by Grothendieck that is called variational Hodge conjecture. That claims that if delta is an algebraic cycle, then delta t is an algebraic cycle for every t in the Hodge locus. Right? This, as Ananio explained before, this is clearly true if we believe in Hodge conjecture, right? Well, it's not that clear. It's not absolutely clearly true that if we believe in Hodge conjecture, because we are taking integer coefficients, not rational coefficients, but it's possible. It's not too hard. So, well, determining components of the Hodge locus is it's kind of analogous to proof variation of Hodge conjecture for some fixed algebraic cycle in a fixed fiber of this family. So what we will do is study this Hodge locus, and we will prove that in some cases this Hodge locus is smooth, is reduced, and furthermore we will prove variation of Hodge conjecture in certain cases. So in order to do that, we will use the first order approximation of this Hodge locus. So I want to recall a theorem. So I don't know if you do it here or there. So let's do it here. Theorem. This is a theorem due to Carlson, Green, Griffiths, and Harris. This is in 1983, I think, or 63, 83. Okay, this is part of the development of infinitesimal variations of Hodge structures. And it's as follows: if we identify the tangent space of the parameter space of degree d hypersurfaces of Pn plus 1 with the vector space of polynomials of degree d, then we have a nice description of the Hodge, of the tangent space of the Hodge locus, and it is like this. The tangent space of the Hodge locus is exactly the following thing. It's the set of polynomials of degree d such that the integral over delta of the following forms, the residue p times q times the standard top form, xi dx0, here you take out dxi dxn plus 1, is formed with pole along the variety of order f on over 2 plus 1 is 0 for every q polynomial of degree d times n over 2 minus n minus 2. Right? So, well, this is a classical result of Griffiths. We know that in the case of hypersurfaces, we have an explicit basis for the primitive part of the Rham cohomology of the middle degree of any hypersurface, and the basis is given exactly by these forms of this type, right? You consider a meromorphic form in the projective space with pole along x, and depending on the order, you will end up in a different place in the Hodge decomposition of the hypersurface, right? So here we're taking the pole of order n over 2 plus 1 to end up in the middle part of the Hodge decomposition of the corresponding hypersurface. Sorry, here I didn't tell you what is f. F is exactly the equation of this guy. This is f equal to 0 inside Pn plus 1. Okay, this result is a classical result. It is a combination of Griffiths basis and the fact that infinitesimal variations of Hodge structures is correspond with polynomial multiplication that is encoded here in the case of hypersurfaces. Okay. So this kind of result was the one that inspired Hossein to define the following Artinian Gorenstein algebra associated to the Hodge cycle. So, well, after Dan's article, yeah. No complaints? Okay. Well, maybe this is not Hossein's contribution. I don't know. Well, it seems. Okay, definition. So, again, let x f equal to 0, a smooth hypersurface of degree d, even dimension n, and delta Hodge cycle. Okay, so we define the following ideal, J f delta. It will be an homogeneous ideal, so we define it in each homogeneous piece. We define it as the set of polynomials of degree I, such that the integral over delta of the residue of p times q times this form omega, this is the standard form, I equal to 0 to n plus 1 minus 1 I x I dx I hat over f n over 2 plus 1 is equal to 0 for every q in degree every q in degree sigma minus I, where sigma is equal to d minus 2 times n over 2 plus 1. And, well, you define it like this if I is less than sigma, and for I bigger than sigma, you define it as everything. Okay, so this ideal defines an Artinian Gorenstein algebra, and that is not so hard to see. In fact, well, by Macaulay's theorem that I'm about to erase, the moral of Macaulay's theorem is like this. You take a variety defined by exactly n plus 1 equations in the projective space, and such that it defines the empty set. So the algebra associated to this will be an Artinian Gorenstein algebra. And the suckle will be of this Artinian Gorenstein algebra. The suckle will be this number sigma. Okay, but I want to explain why is that true. So this is well, it is quite elementary to see that this will define an homogeneous ideal. I mean, this J f delta is an homogeneous ideal. That's elementary. To prove that it is that the quotient is an Artinian Gorenstein algebra is also possible to see when you using Poincaré duality. But I want to give a more detailed description of this ideal. So what does that mean that this integral is equal to 0? So the integral of the residue of p times q omega over f to the n over 2 plus 1 is exactly this following thing. So this will be the integral over x of the residue of this thing, which the Poincaré dual of this cycle, when you look at it in the Rham cohomology, and not only the Poincaré dual, but the primitive part of this thing, right? Because if this has some multiple of the polarization, then since this is in the primitive cohomology, the integral of this will be 0, right? So you can take here the primitive part of this guy. I don't know, I will put it. I don't know if this notation is useful, it's useful, but I will use it. So, and the thing is that we know that this guy here belongs to the n over 2 part of the Rham cohomology in primitive cohomology. And Griffith's theorem tells us that there must be a polynomial such that this guy is the residue of this polynomial associated to delta times omega over f to the n over 2 plus 1. So this polynomial exists, and this polynomial is a polynomial, homogeneous polynomial of degree d minus 2 times n over 2 plus 1. The same number that the circle of this idea. So there is a theorem due to Carson and Griffiths around the 80s that tells you that this will happen. So you will have this this equation is 0 if and only if this product of polynomials pq times p delta belongs to the Jacobian ideal of f. This is the ideal generated by the partial derivatives of the polynomial f, the Jacobian ideal. This is Carson Griffiths. In particular, we conclude that the homogeneous part of the Jacobian of this ideal is exactly the set of polynomials p in degree d such that p times q times p delta is equal to 0 in the Jacobian ring Rf, the Jacobian ring C of x modulo the Jacobian ideal for every q with degree d times n over 2 minus n minus 2. Okay, so by Macaulay's theorem, it is easy to see that the Jacobian ideal defines Artinian Gorenstein algebra, right? Because, well, it is a smooth hypersurface. So the zero set of the partial derivatives of f will be empty. So by Macaulay's, we know that Rf is Artinian Gorenstein algebra of so-called, it will be the sum of 1 less the degree of each partial derivative. It will be exactly d minus 2 times the amount of variables that is n plus 2. Right? This is 2 times sigma, 2 times this sigma. And since this is an Artinian Gorenstein algebra, we know that the multiplication is a perfect pairing. So if p times q times p delta is 0 for every q, that means that p times p delta must be 0 in the Jacobian ring, right? So this is exactly the Jacobian ideal of f divided by p delta in degree I. Okay? So what we see here, well, right now it's trivial to see that Rf delta is an Artinian Gorenstein algebra. In consequence, this Rf delta, that is exactly the ring of polynomials divided by Jf divided by p delta, is Artinian Gorenstein algebra of so-called sigma. And furthermore, well, by this theorem, furthermore, we know that the degree d part of this ideal corresponds to the tangent space of the Hodge locus associated to this Hodge cycle. Okay, so when we try to prove variational Hodge conjecture, when we try to say something about the smoothness or reducedness of the Hodge locus, what we usually do is to look at the first order approximation. We look to this Zariski tangent space of this Hodge locus, and that means that we're using just a partial part of the information given by this ideal, just the degree d part of this ideal. So what I want to explain now is that, in fact, we can compute this whole ideal, and we can use all the information of this ideal to get some extra results. For instance, there is a theorem. There is a theorem that I did in my thesis, that I compute this polynomial, this p delta, in the case of complete intersection cycle. I mean, if delta is the cycle corresponding to a complete intersection, let's put like this, where so set is f1 equal to 0, f2, fn over 2 plus 1 equal to 0, a complete intersection of dimension n over 2 inside X, and X is given by f equal to 0, then I can compute this polynomial. This p delta is exactly the determinant of the Jacobian matrix associated to the following polynomials: f1, g1, f2, g2, fn over 2 plus 1, gn over 2 plus 1, where f is equal to f1 g1 plus f2 g2 plus fn over 2 plus 1 gn over 2 plus 1. So in the case of the algebraic cycle delta is a complete intersection cycle or is a combination of complete intersection cycles, I can compute explicitly this polynomial p delta. Okay. So I want to give you now I want to give you a sketch of proof of how you can use this information to prove variational Hodge conjecture in certain cases. So first of all, I want to I don't know, make an, it's not an example, it's a remark. Okay, so first, variational Hodge conjecture is true for several cases. One of these cases is when the algebraic cycle delta, so variational Hodge conjecture is true in the case of hypersurfaces. When you deform, when you take delta, Hodge cycle inside a smooth degree hypersurface such that it is supporting a complete intersection cycle, where C is complete intersection. This result is basically due to Otwinovska with an asymptotic approach, and well, this is 2003, and then 2014, where he in fact proved this result. Okay, furthermore, we know that the Hodge locus, the Hodge locus is smooth and reduced. Well, why am I saying that this is smooth and reduced? I mean, this locus has a natural analytic structure, right? Since it is parametrizing the parameters where the deformation of this cycle remains Hodge, it will be naturally defined by the zero set of equations, holomorphic equations, given as, so this will be exactly the set of zeros of forms, I don't know, omega 1, omega k, delta t equal to 0, where this omega 1 to omega k are elements in the Rham cohomology bundle associated to the family, are sections of the Rham cohomology bundle such that they form a basis for the filtration Fn over 2 plus 1 in each point T. Right, well, in a neighborhood of 0. So these functions are holomorphic functions, so you have a natural analytic structure on this thing, and this analytic structure may be non-reduced, may be smooth, right? So it's non-trivial to say this is smooth and reduced, but this is a fact proved by Dan in 2014. Well, if I have time, I can give you an idea of how you can recover this result by using this Artinian Gorenstein algebra in an easy way. But I want to move further and go to the the main theorem I want to present today. So this is as follows. So now, since the complete intersection case is already known, we consider other cycle that is not supported in a complete intersection, in one complete intersection, right? So variety, right? So we consider the following case. So let T check inside T. Here recall that T is the parameter space of smooth hypersurfaces. Right? This is inside the polynomials, homogeneous polynomials of degree D. And I will take this guy to be the parameters T such that the corresponding hypersurface xt contains two linear subvarieties, Pn over 2 and Pn over 2 check contained inside it, such that they intersect in a fixed dimension, in a previously fixed dimension. This is Pm for a fixed m. Okay, so you can think that this is Tm. Okay, so I'm just taking the hypersurfaces that satisfy this. Okay, so in this subspace, I claim the following. So if M, well, I will separate it in two parts. First part, if this fixed number M is less than n over 2 minus d over d minus 2, then for any integer numbers a, b different from 0, and for a general point 0 in T bar, in T check, so the Hodge locus corresponding to delta defined as A P n over 2 check, a linear combination of these two linear cycles, then the Hodge cycle will be exactly the Hodge cycle corresponding to each of the linear cycles independently. Furthermore, this Hodge locus will be smooth and reduced. Furthermore, it is smooth and reduced. And the second part is as follows. In the other case, if m is greater or equal than n over 2 minus d over d minus 2, then the Hodge locus B delta is singular, non-reduced, or or strictly bigger than this Hodge locus corresponding to each linear cycle independently. And this guy is smooth and reduced, which is always smooth and reduced. Sorry, here if this is bigger or equal than this, and 0 in T check corresponds to the Fermat variety. So this happens. B delta, the Hodge log associated to this linear combination is or singular or non-reduced or is strictly bigger than this. So that means that in this case, if the Hodge log is non-singular and reduced, well, this might be explained by the fact that this algebraic cycle is homologous to another algebraic cycle that has a higher deformation space than just deforming each of the linear cycles independently, right? So I want to give a sketch of proof of this result. So the history of this problem is that we consider it first by computer assistance, and we obtained this situation. We realized that for some combinations and some cases, we obtained a smooth and reduced Hodge locus, but in some other cases, we obtained some non-reduced Hodge locus, and the situation was very strange. So using this Artinian Gorenstein algebra, it was possible to produce this theoretical proof and understand a little bit more what is happening here. Okay. Yeah, it's general. It's not in a neighborhood of Fermat. It's for a general. In a Zariski open set of this guy. Not necessarily a neighborhood of Fermat. Sorry? I don't understand. I don't understand. I mean, this result is for a Zariski open set of this T bar, right? And this Zariski open set is not necessarily a neighborhood of Fermat. We cannot prove that. I can just prove that it's a Zariski open set. I also know that this is true for the point Fermat. But what I cannot prove is that for every branch passing through Fermat, there is a neighborhood of it. I just know that for one branch passing through Fermat, there is a Zariski open set or an analytic neighborhood of this guy where this is true, right? So I need to check all the other components passing through Fermat, and I didn't do that. Okay, so how do you prove this statement? We already have all the tools, all the necessary tools to do this. So a sketch of proof. So the first reduction is to reduce everything to Fermat. I mean, if we know that it is true in Fermat, if we assume it for delta the Fermat variety, then we can conclude that it's true in a Zariski neighborhood of Fermat. And I want to explain a little bit this. So consider H, the space parametrizing the triples xt, Pn over 2, Pn over 2 check belonging to T times the Grassmannian of n over 2 subspaces of the n plus 1 projective space squared, satisfying the properties, right? Such that they are contained in xt, and they intersect in Pm, right? So this space is a finite cover of T check, right? This is branch cover, fine. So we can define the following function. So we have this function phi that goes from here to this vector space, the cell linear transformations of the space of homogeneous polynomials of degree d to the dual or maybe bilinear maps d n over 2 minus n minus 2 dual, right? So we define it. This is a map that for every triple will give you a bilinear map that goes from this vector space times this vector space to C. And we can define it in terms of basis. Well, we have basis here, so you define it this way. I will define it here. So you can define this map in this following way. So you define it like this. We will define it as a matrix, the matrix of integrals over the cycle we are considering of the residue of p, q, omega over f n over 2 plus 1, where p is in degree d and q is in degree d times n over 2 minus n minus. Okay, so this is a regular map. This map is regular, so it's discontinuous in the Zariski topology. So if we take the kernel of this function for every point here, so the kernel, the dimension of the kernel is the places where the dimension of the kernel is constant will give you a locally closed subset of H, right? So this is constant. This is constant in a locally closed in Zariski topology, a subset of H, right? So if we know that the theorem is true for the Fermat variety, since the Hodge-Locus system moves and reduce, what we get is that in fact in a small neighborhood of the point corresponding to Fermat, in here, in an analytic neighborhood of this guy, we will have a constant rank of this kernel here. So since we know that this is true for an analytic neighborhood, it must be true for an Zariski neighborhood, right? Because, okay, so this is the first reduction. So now we just focus on the Fermat point. So for Fermat, the second thing that we have to prove that is an elementary problem of algebraic geometry is that the second fact is that the dimension of B Pn over 2 intersected with B Pn over 2 check is equal to the dimension of the tangent space of each one intersection of the tangent space. Okay, so in particular, this guy is smooth and reduced. The intersection is smooth and reduced. And the tangent space of this thing is exactly this intersection of the tangent spaces. Okay, so this is elementary. And after all this, the only thing that we have to do now, so this reduce the problem to prove that the Zariski tangent space of B delta is equal to the Zariski tangent space of this intersected with the Zariski tangent space of the other linear cycle. Right? And what we know is that this is exactly JF divided by some polynomial here. Well, this guy is exactly JF divided by some polynomial P1 in degree D. This is JF divided by some polynomial P2 in degree D. And I know how to compute these polynomials since I know the equations of these linear subvarieties of the Fermat variety. In the case of Fermat variety, all this is explicit. I can compute these polynomials with my previous theorem. And this will be the sum of these two guys. Here I am putting inside P1 the constant A, and the constant B is going inside P2. So you reduce the problem to a purely algebraic, commutative algebra equality between ideas. And when you write down the polynomials, in fact, the polynomials are quite simple. Sorry? Yeah, but I am putting A inside P1, right? So, for instance, we can take, for example, we can take Pn over 2 to be this equation, x0 minus zeta 2d x1 equal to 0, xn minus zeta 2d xn plus 1 equal to 0. This is a primitive root of unity. And we take the Pn over 2 check to be the same thing in some variables, and the other you can vary the exponent of this thing. So you take something like this. Equal to, and then you repeat the other equations. Right? And we can compute the polynomials. So the P1 will be exactly R1 times Q. P2 will be R2 times Q, where R1 is the product of xk to the d minus 1 minus zeta 2d xk plus 1 to the d minus 1 divided by xk minus zeta 2d xk plus 1, where k is, where k is, well, here times a constant, non-zero constant. K is greater or equal than n minus 2m and is even. And for R2, you have the same things, but you add here the exponent. R2 is similar with the exponent. And Q is the rest, right? Q is the other product, the product of the same thing. But here K is less than n minus 2 even, right? And R2 is a constant times K n minus 2m even. The same thing except but the exponent here. Okay, so to prove that algebraic equality, well, to prove the theorem, in fact, is equivalent to show that this equality holds if and only if. So this equality holds if and only if d is less than d minus 2 times n over 2 minus m. And after you write down the polynomials and you see that they have this common factor, that equality is equivalent to show that I divided by R1 in degree d intersected with I divided by R2 in degree d is equal to I divided by R1 plus R2 in degree d if and only if d is less than d minus 2 n over 2 minus m, where I is the ideal obtained by quotient of the last part. I mean, you're forgetting the equations corresponding to Q. Right, so this is just considering x0 to, wait, I think I made a mistake. Yeah, this is the other way. This is less, and this is d. x0 to d minus 1, and xn minus 2m minus 1 to the d minus 1, right? This is exactly the same. Remember that we're working in Fermat variety, so the Jacobian ideal is this, right? So we can, when we work algebraically, we can forget about these last equations, and this inside this polynomial ideal, polynomial ring of n minus 2m variables, this is also defining an Artinian Gorenstein algebra, right? So this ring here, defined in this way, is Artinian Gorenstein algebra of socle exactly d minus 2 n over 2 minus m. So the only thing that you have to check now is that when you take two of these quotients, the intersection will coincide everywhere except in the degree of the socle, except exactly in the degree of the socle. And that's a tricky, commutative algebra problem. Here, you have everything explicit, right? The monomial ideal is explicit, the polynomials are explicit. You play a little bit with this and you prove it. And well, I think that this might be done in more general context. I mean, not just the Fermat variety. The Fermat variety is easier because your ideals become monomial ideals. So, but well, I think that's all. I have more time or no? Okay.